Hey everyone, today I want to talk about complex numbers and in particular how we can perform arithmetic operations on complex numbers. So the first question naturally is, what is a complex number? Well, a complex number is a number of the form a plus bi, where a and b are real numbers. And for those of you who may have forgotten, I is defined to be the square root of -1, and I is known as the imaginary unit. Okay, so that seems simple enough, but before we get to complex arithmetic, I want to explain the concept of the real and imaginary parts of a complex number. So what is the real part of a complex number? Well, we denote that by saying RE and then placing the number in question inside the parentheses, and this indicates that we want to take the real part. So the real part of a complex number is the number that is not being multiplied by I. So in this case, that number is A. So a is the real part of a plus bi. Now, what about the imaginary part? Well, the imaginary part of a complex number is probably what you'd expect. It's the number that is being multiplied by I. So in this case, that number is b. Perfect. So we now know how to take the real and imaginary parts of a complex number. Now let's go ahead and dive into complex arithmetic. So the first operation I want to focus on is complex addition, and I think that's the easiest to understand. So how exactly do we add two complex numbers? Well, I think the easiest way to tackle this is to do this by example. So let's say we want to add the number 1 plus I to the number 3 plus 2I. How exactly are we going to do this? Well, we want to add the real parts of the numbers and the imaginary parts of the numbers separately. So the real part of 1 plus I is 1, and the real part of 3 plus 2I is 3. So we're going to do 1 plus 3 is 4, and this is going to be the real part of our solution. So we have 4. Now let's go ahead and add the imaginary parts. So we have 1I plus 2I, and that's going to give us 3I. So 4 plus 3I is the solution to this addition problem. Okay, now let's go ahead and move on to subtraction, and it's basically the same thing, but we're just going to subtract the real and imaginary parts instead of adding them. So we're going to go ahead and do 1 plus I minus 3 plus 2I. So again, we're just going to subtract the real and imaginary parts. So we have 1 minus 3, that's going to give us -2. And then we have I minus 2I, and that is -I. So -2 minus I is the solution to our subtraction problem. All right, now how can we go ahead and do complex multiplication? Well, we're going to use the method that you probably learned in algebra, and that is FOILing. So let's say we want to do 1 plus I times 3 plus 2I. Well, we're just going to multiply each number in the first number by each number in the second number, and that's going to give us our solution. So let's go ahead and do that. We have 1 times 3 is 3. 1 times 2I is 2I. And then we have I times 3 is 3I. And then I times 2I. Now let's stop for a second and think about this. I is equal to the square root of -1. So what happens when we have I times I? Well, we have the square root of -1 squared. So the square and the square root cancel out, and that just leaves us with -1. So therefore, 2I times I is going to be -2. So we're going to have a -2 right here. So notice that we can go ahead and combine like terms. So we're going to have 3 minus 2 is 1. And then 2I plus 3I is 5I. So 1 plus 5I is our solution. Now, for the last operation, we're going to do complex division. So how can we go about dividing two complex numbers? Well, in order to do that, we need to understand the concept of the conjugate of a complex number. So what is the conjugate? Well, let's do it by example again. Let's say we have the complex number 1 plus I, and we want to take the conjugate. Well, all one has to do this is to flip the sign of the imaginary part. So instead of 1 plus I, the conjugate will be 1 minus I. Perfect. And let's say you wanted to take the conjugate of 1 minus I, well, you would just flip the sign of the imaginary part again, and it would bring you back to 1 plus I. So that is the concept of the conjugate of a complex number, and we're going to go ahead and use that to our advantage to do complex division. So let's say we want to do 1 plus I divided by 3 plus 2I. Okay, so in order to do this, we're going to multiply the numerator and the denominator by the conjugate of the denominator. So the conjugate of the denominator is 3 minus 2I because we need to flip the sign of the imaginary part. So we're going to multiply the denominator by 3 minus 2I and the numerator by 3 minus 2I. Now notice that I'm allowed to do this because 3 minus 2I over 3 minus 2I is equal to 1. So we're just multiplying the original number, by 1, which doesn't change the result. So let's go ahead and FOIL the numerator and the denominator and see what we get. So we have 1 times 3, which is 3. 1 times negative 2I is negative 2I. We have I times 3 is 3I. And then I times negative 2I. Remember that I squared is negative 1, so we really have negative 1 times negative 2, which is positive 2. Okay, so this is the numerator. Let's go ahead and find the denominator. So 3 times 3 is 9, and then we have 3 times negative 2I is negative 6I, and then we have 2I times 3, which is 6I, and then we have 2I times negative 2I. So I squared is negative 1, so we have negative 1 times negative 4, which is positive 4. Perfect. Now let's go ahead and combine like terms and then simplify the fraction, and we can go ahead and get our new complex number. So 3 plus 2 is 5, and then we have negative 2I plus 3I, which is 1I, or just I. So we have 5 plus I in the numerator, and then in the denominator, notice that negative 6I plus 6I equals 0, so those cancel out, and we're just left with 9 plus 4, which is 13. Okay, let's expand the fraction out to get it into separated real and imaginary parts. So we can write this as 5/13 for the real part plus 1/13 I for the imaginary part. And there we go. That is the solution to this complex division problem. And that is how you perform complex arithmetic on complex numbers.